In these notes, we're going to look at the fundamental theorem of algebra, the linear factorization theorem. We're also going to define some notation and vocabulary. We're going to learn about the multiplicity of zeros, and then we're going to go through a bunch of examples of solving a lot of more complicated polynomial functions than you've seen before. We're going to build up polynomial functions from the zeros we're given. We're going to look at the intermediate value theorem and some more examples of that, and then just a lot more examples of solving big polynomial functions. So the fundamental theorem of algebra says if f of x is a polynomial of degree n, that means that the first term would be like something like x to the n power, where n is greater than 0. So obviously it can't be x to the 0 power, or it wouldn't be a polynomial. So x to the n power, then f has at least one 0 in the complex number system. And it says complex makes you think of imaginary numbers, but remember complex can also mean real. So all the fundamental theorem of algebra really says, if you were to simplify this down, it just says if you have a polynomial function of some degree, you're guaranteed to have a solution. So that's important because that just means every polynomial problem that I give you, you should be able to find a solution. The linear factorization theorem says if f of x is a polynomial of degree n, so we're dealing with the same thing again, where n is greater than 0. Okay, so f has precisely n linear factors. So remember, it's degree n. That means that whatever the degree of the function is, that's how many solutions it has. So you could write that the degree of the function tells you how many factors or solutions there are for that polynomial. All this stuff that's written out here is just showing you that we could have some leading coefficient that doesn't really do anything for us, but then all of these linear factors are just x to the first power minus some number. They're calling it a complex number again because it could either be real or imaginary. So if x minus c1 is a factor, that means x equals c1, c1, that would be your solution. And we're going to use this fact a lot. So in the next section, we're just looking at some notation and vocabulary. Here it says x equals a in both of these boxes. And the first one is the solution, the second one is a 0. They mean the same exact thing. We call them zeros because it's where we get the x value where it would cross on the x-axis, and on that point it would be like a comma 0, which actually brings us over here, right? That's how you'd write an x-intercept. And again, all of these solutions, like if it was a solution of x equals a, that would come from the factor x minus a. So all of these things are related. You just have to be comfortable reading and writing them in all of these different formats, and if we ask you to write the linear factorization, you would write all of the factors like this. If we ask you to find all of the solutions, make sure you write them as x equals numbers, and if we say find the x-intercepts, make sure you write them as coordinates. The next section of notes is just defining multiplicity. So it says we have a factor x minus a to the k power, where k is greater than 1. So this isn't just like x minus a to the first power. This is like if you have a polynomial and you factor it down, you have like x minus something squared. So that factor is repeated. Or it could be x minus a to the third, so you'd have that factor 3 times. So it says it yields a repeated 0, x equals a, of multiplicity k. So all that means is whatever the exponent is on that factor, that's how many times you have that solution. Now here's the important part. If k is an odd number, let's just use an example. Let's say we had x minus 3 to the third power. Anytime it's odd, it's going to cross the x-axis at that point. So this is going to have an x-intercept. Actually, let's write it as a point. So it would be 3, 0, but it's going to cross through the graph at this point, since it's an odd multiplicity. So there'd be a point there, and a cubic function usually looks something like this. So this is just a really rough sketch. But it's going to cross through the graph. Whereas if k is even, if it's an even multiplicity, then the graph is just going to touch the x-axis and then bounce off. It doesn't actually cross through the x-axis. So for instance, if it factored down to like x plus 2 to the fourth power, then it's going to have an x-intercept of -2. But since it's even, it's not going to cross through the graph there. It's just going to bounce off. So the graph would actually look like this. So odd multiplicities cross over the x-axis, and even multiplicities just bounce off the x-axis. Let's look at an example of that. So I have -2t to the fourth plus 2t squared. So the first thing I notice is that they both have a 2 in it, and actually since the first thing is negative, I'm just going to pull a -2t squared out of both of these terms. So that would leave me with just t squared, and then minus, I guess, just 1. So let's just double check that. -2t squared times -1 would be positive 2t squared. So there we're good. All right, and then t squared minus 1 is a difference of squares. So this actually factors down to -2t squared times t plus 1 times t minus 1. So this function is a fourth degree polynomial, And we didn't say this anywhere in the notes, but the number of turns is always 1 less than the degree. So I'm just going to write 4 minus 1, which is 3. That means that this graph could turn around, like if it's going up, then it would turn and go down, then if it's going down, it would turn and go up. It could turn around up to 3 times. It doesn't have to have exactly 3, it could just have up to 3 turns in it. So now let's look at the multiplicity of the zeros that we get from this factorization that we did. So this is the first factor, negative 2t squared. If I took that and set it equal to 0, I could just divide that negative 2 out and it would just disappear. And then t squared equals 0. If I take the square root of both sides, t still just equals 0. But it happened twice because it was degree 2. It's kind of like taking the square root of 0 and getting plus or minus the square root of 0, but we would still just write 0. So t equals 0. But I'm going to say that's a multiplicity of 2. That means on the graph, it's going to have an x-intercept of 0, but it's not going to cross the graph there. It's just going to bounce. So maybe it goes like this, or maybe it's bouncing down. I'm not sure yet. So let's see what else we can figure out. This factor, t plus 1, that would give me an x-intercept of t equals negative 1. And that just happens one time. I just have that factor once. It's to the degree, or it's to the power of 1. But the other factor would give me t equals positive 1, and again that also has a multiplicity of 1. So I know there's x-intercepts at negative 1 and positive 1. Alright, now we have to look a little bit farther into this function to see what's going to happen. So it's an even degree polynomial. That means that both ends of the function are going to go in the same direction. So maybe they both go up, or maybe they both go down. And the other important thing is the leading coefficient in front of that term with the highest degree, or the highest power, is negative. So that means that both ends of this function are going to go down. So I want it to go down here and down here. So now if I want to cross through these x-intercepts and go down to the left, down to the right, I know the function's going to look something like this. And I wanted to bounce off that in the middle, so there's my function. The only thing I'm not sure of is how high these bumps in the middle are going to go, but I know it's going to cross here, bounce, and then cross there. And remember when we were talking about the turns, you can see that from left to right, it's going up, 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 and then turns once, turns twice, turns 3 times, and then just goes down forever. Let's see what we can do with g of x. So now I'm going to pull a 2 out of every one of these terms, and that would leave me with x to the 4th minus x squared minus 20. And then let's see what I can do with what's left here. So I think I can factor this into x squared and x squared. And then, let's see, I think if I do minus 5 and plus 4, that would give me negative 20 if I multiply them, and yep, negative 1 if I added them. Now, I would want to try to factor this farther to get to just linear factors, but unfortunately x squared minus 5 isn't a difference of squares, and x squared plus 4 is also not a difference of squares. So I'm not going to be able to factor this any farther, so I'm just going to have to set these equal to 0 and solve. I'll do that in just a second, but let's fill out some of this information below. So it was a 4th degree polynomial, and that means that if I subtract 1 from that, 4 minus 1 would be 3. So this could have up to 3 turns in it. So over here I'm just going to set x squared minus 5 equal to 0. That means x squared equals 5. That means x equals plus or minus the square root of 5. And then x squared plus 4 equals 0. So x squared equals negative 4. And now if I take the square root of that, this is going to be imaginary now. So plus or minus, and the square root of 4 is 2. So this would be 2i. So there's my 1, 2, 3, 4 solutions. The only problem is these two are real, so I'm going to have x-intercepts there. These two are imaginary, so I'm not going to actually see where it's crossing the x-axis at those solutions. So I could write these as x-intercepts like the square root of 5 comma 0 and negative square root of 5 comma 0, and each of those just happens once. Like the factors weren't repeated, so these just have multiplicity of 1 for both of them. And same thing for the imaginary solutions, except for I can't write those as x-intercepts because it's not going to cross the x-axis. I can't graph imaginary numbers. But I will write that these each have a multiplicity of 1. Now if I'm estimating this x-intercept just to see where to graph it, the square root of 4 is 2, so that means that the square root of 5 should be a little bit more. I'm just going to estimate maybe 2.1. It really doesn't matter what value it is exactly. I just have to graph this at negative 2 and a little bit more and positive 2 and a little bit more. So it's going to cross the x-axis at those points, and I'm not sure where this really shows up on the graph. So let's look at the degree and think about the end behavior. So it's an even degree. That means it's going to go in the same directions, like both up or both down. And this is a positive leading coefficient, so both ends are actually going to go up. So it's going to go like up to the left and up to the right. that means the graph is going to look like this. And I'm going to say probably somewhere in the middle it has a turn like this. And this is where your imaginary solutions would come from. It's just not crossing the x-axis. So your graph would probably look something like a W like this. Here we're going to look at very different types of problems. So it says write a function with the given zeros. Well, if 2/3 is a zero or a solution, that means x minus 2/3 would be a factor that that solution would come from. If -4 is a solution, that means x plus 4 would be the factor that comes from. I'm always just changing the sign, so it's like x minus whatever the solution is. Now you could write it this way, but it's nicer to write factors that don't have fractions in them. So if I wanted to get rid of this fraction with a denominator of 3, I'd have to just multiply that factor by 3 and just distribute that 3 in. So that would be 3x minus, and then these 3's would cancel, and they'll just give me 2, and then x plus 4. And if you want to double check that, you could take 3x minus 2, set it equal to 0, so then 3x equals 2, and then x equals 2/3, and yep, that works out. That ended up being what we wanted up there. So this is just a nicer looking way of writing that factorization. And don't bother foiling that together or multiplying these factors together, because it looks nicer this way, and this tells us a lot more about the function. It tells us that it has these zeros. The next one just has more solutions. So the first one would be x minus 0. Actually, you don't even have to write the minus 0, so just x. And then x minus -3 would be like plus 3. And then x minus 3 and x minus 4. So there's our 1, 2, 3, 4 solutions. So we have 1, 2, 3, 4 factors. And again, don't bother multiplying it together. You could just leave it this way. However, if you did want to write this out as a polynomial in standard form, I just want to show you that quickly. So like these first two factors, I'm going to multiply these together because that just involves distributing this x into that parentheses there. So that'd be x squared plus 3. And then if I multiply these together, I guess I could use a box for that. So that would give me x squared minus 7x plus 12. And now I'd have to take this quadratic factor and multiply by this quadratic factor. So again, I'm going to put a box underneath this, but this is just two terms in front. So the polynomial altogether in standard form would be x to the 4th. Let's see, let's look for x to the 3rds. I guess it's just this one, so minus 7x to the 3rd. But then there's 3x squared, 12x squared, so plus 15x squared, minus 21x, plus 36. And you could write your answer that way as well. For number 3, just don't be confused by the way this is written. Some people might think that this is 1 plus or minus the square root of 3, but this would just be 2 solutions. This, what we're given here, is actually 3 solutions. We have 1 and then plus or minus the square root of 3. So I could write x minus 1 and then x plus the square root of 3 and x minus the square root of 3. Oops, the square root of 3. Those would be our factors. I could write my answer this way, or I could multiply these together, and I'm going to choose to multiply these two factors together first because I noticed they're conjugates, so that means that I'm going to get a nice result. So this should be x squared, this and this will cancel, and square root of 3 times negative square root of 3 is negative 3. So that means I just have x squared minus 3, and I just have to multiply that by the x minus 1 in front. So x cubed minus x squared minus 3x plus 3, and that puts it in standard form so that the degrees are always decreasing. The intermediate value theorem is kind of interesting. It says if f is a function which is continuous at every point of the interval from a to b. That means that like we're graphing, let's say a is here and b is here. That means the function is continuous. There aren't any holes or vertical asymptotes or any weird things happening between a and b. And it says if f of a is less than 0 and f of b is greater than 0. So think about like if over here the y value is negative and then over here the y value is positive, well, somewhere in the middle, if it's continuous, it has to cross over 0 at some point. All this means is that if we can find a negative y value and a positive y value, somewhere in the middle there's going to be an x-intercept. So we might want to write something like there must be an x-intercept somewhere between a positive and a negative y value. So let's look at an example. So you could plug any polynomial function into your graphing calculator and then pull up the table, and then let's say you get something like this. So we're going to look at the y values first. So let's see, I've got positive 170, positive 35, but then I have negative 2. So between positive 35 and negative 2, the y value has to be 0 somewhere in there. That means that somewhere between negative 2 and negative 1, there must be an x-intercept. So we're looking at the y values to find the x intervals. And we've learned interval notation, so that means like somewhere between negative 2 and negative 1, there's a solution. So I'm going to write it in interval notation. I'm going to use brackets, which technically mean we're including -2 and -1, and I know that there isn't an x-intercept at those endpoints, so I don't have to include them, but by using brackets, it's going to look like an interval and not look confusing like a coordinate. So back to the table, I go from -2 to -1, so it stays negative. From -1 to +2, though, that's switching, so somewhere between a negative and a positive, there must be a 0 in there. So that means that between 0 and 1, there's another x-intercept. So I'm going to write that interval 0, 1 with brackets. Alright, so then from 2 to -5, that's crossing over 0 at some point. That means somewhere between 1 and 2, there must be an x-intercept. So I'm going to write that with brackets 1, 2. Are there any others? So then from -5 to -10, that stays negative. -10 to +23, yep, that must cross over 0 at some point. So there must be an interval between 3 and 4 where there's an x-intercept. So now we're going to take a break from the intermediate value theorem and go back to solving polynomial functions. So it says use division to show that x is a solution of the third degree polynomial equation. Use the result to factor the polynomial completely. List all real solutions of the equation. Alright, so there's a lot going on here. If x equals 2, that means x minus 2 is a factor that solution came from. And if this is a factor of this polynomial, that means that I should be able to divide it. So I'm going to put x minus 2 in front and start doing long division with this and see what I get. So x cubed will go in the box and we'll start our long division process. So x squared would go on top, x times x squared is x cubed. This would be -2x squared. But I want to have no x squared, so I'm going to have to add 2x squared to cancel that out. So then x times 2x gives me 2x squared. This would be -4x. Alright, but I want to have -7x, so that means I have to subtract 3 more x. So then this would be -3 times x is -3x. -3 times -2 is +6. And thank goodness that works out. I wanted to have +6 there. So if this didn't work out, then I'd have a remainder, and that means that this wouldn't be a factor. But it says that x equals 2 is a solution, so that means this is a factor, so that's good. We don't want to have a remainder. Also, we're left with this quadratic, x squared plus 2x minus 3. And that's awesome because I know how to solve quadratics. I'm going to try to factor this into, let's see, something that multiplies to -3, so like +3 and -1, and yep, that multiplies to 2. So that's great because then I can get 2 more solutions out of this. X equals -3 and x equals +1. So there's my 3 solutions. It said it wanted me to factor the polynomial completely, so let's write out those factors all together just so it looks like it's all one polynomial. And then my solutions were just x equals 2, x equals -3, and x equals 1. Alright, the next problem is very similar. It says verify the given factors of the function, find the remaining factors, use your results to write the complete factorization of the function, and list all zeros. So it's a third degree polynomial, but they gave me 2 linear factors. So if I divide both of those out, I should be left with just 1 more factor. By the way, this would give me a solution of x equals -3 and x equals 2. So we're very close to being done, actually. So I'm just going to take the first factor, x plus 3, and write that out front, and start the long division. So 3x cubed goes in the box. This would be 3x squared, which would make this 9x squared. But I only want to have 2x squared, so I'm going to subtract 7x squared. So then x times -7x gives me that. This would be -21x. Alright, -21, but I want to get to -19x, so I'm going to add 2x. Alright, x times 2 gives me that, which makes this 6, which is perfect because I want to have 6, so there's no remainder. Also, that gives me 3x squared minus 7x plus 2. And if I take this quadratic, I should be able to divide that by this last factor and see what I'm left with. Alright, so I'm going to put x minus 2 in front of a box and put 3x squared in. So then this would be 3x. This would give me -6x, but I want to have -7x. So I'm going to subtract 1 more x, which means this would be -1. -1 times -2 is +2, and that's perfect because that's what I want. So the last factor was 3x minus 1. So let's write that up here. And there's my complete factorization of f. And all of the solutions, this last one would be x equals, well, I'd have to add, if I set this equal to 0, I'd have to add 1 over and then divide by 3, so 1/3. And there's all my 3 solutions. The next example says find all the zeros of the function, write the polynomial as a product of linear factors, use a graphing calculator to help you. Okay, so I noticed that as x to the fourth, that means I'm looking for 4 solutions. But there's more than 4 terms here, so I can't use factor by grouping, and I don't have any other algebraic methods of trying to factor or solve this. And it says use a graphing calculator to help you. So I put it into Desmos and got a graph that looks like this. You can't see what's happening in the middle, but it's going way down here and then coming way back up. So what's nice about this is I can see that -6 is a solution and 1 is a solution. Also 1/2, but I'm not going to deal with that quite yet. I'm going to start with these first two, which are nice integer solutions. So if -6 is a solution, that means x plus 6 is a factor of this polynomial. And if 1 is a solution, that means x minus 1 would be a factor. So that's great because I already have 2 factors. If I take this 4th degree polynomial and divide 2 factors out, that would leave me with a quadratic, and I can get my last 2 solutions from that. Also, you might have already saw this and wondered where I was going with this, but this solution, 1, 0, or that x-intercept, it's bouncing there. So that means that it has a multiplicity of 2. It's a repeated 0. So that's even nicer because that means I have x minus 1 as another factor that I could divide out of this. And honestly, I don't want to have to do a bunch of different long division problems. It's going to get messy with a lot of different boxes all over the place. So let's just multiply some of this together really quick. So that's x squared minus 2x plus 1. And I could multiply that by the x plus 6 that I had in front there. So if I combine like terms there, I have x cubed. Let's see, there's 2x squared terms. I have 6x squared minus 2x squared. So that gives me plus 4x squared. I had negative 12x plus x, so that's minus 11x, and then plus 6. So stick with me here. I'm going to put this in front of a box for the long division now. And remember, the thing I'm trying to divide is this original polynomial. So 2x to the fourth is going to go in the box. And let's see what happens now. So what times x to the third is 2x to the fourth? Well, this would be, or actually 2x. So that would make this 8x to the third. Negative 22x squared, and 12x. So let's see, I have 8x to the third. I want 7x to the third, so I'm going to have to subtract 1x to the third. So then x to the third times what is that? That would be negative 1. So then this would be, let's see, negative 4x squared, positive 11x, and negative 6. So now let's compare again. I've got 8x cubed, negative x cubed, that's 7x cubed, that's great. Negative 22, negative 4, that gives me negative 26, x squared. 12 and 11x gives me 23x, and negative 6 gives me negative 6. Perfect, so this worked out. I don't have any remainder, and this is my last factor, 2x minus 1. So I can write that up here, and that makes sense, because if I were to solve this, if I set it equal to 0, I'd add 1 over to the other side, and then divide by 2, I get x equals 1/2, and that's this last solution, 0.5. Here's the last of the big polynomials that we'll have to solve. So it says find all zeros of the function, use a graphing calculator to help you. So I put it into Desmos and I got a graph like this. The important thing is it gives me an x-intercept of negative 0.75. So I could write a factor as x plus 0.75. I'm actually going to write it as 3/4 because then that'll allow me to do the thing I did before with, like, I don't want to have a 4 in the denominator, so I'm going to multiply this by 4. Multiply it in, so that would be 4x plus 3 when the 4 is canceled there. So here's my first linear factor. And if I take this cubic function and I divide one factor out, that will leave me with a quadratic, and I can solve that. And it looks like it only has one x-intercept. The other solutions are up here somewhere, but it's not crossing the x-axis, so they're going to be imaginary. So now I should be able to take 4x plus 3, put that in front of a box, and start this long division to see what I get for a quadratic. So 4x times 4x squared gives me 16x cubed. That makes 12x squared down here. But I want negative 20x squared, so I'm going to have to subtract 12 and 20 more. So that would mean subtract 32x squared. So 4 times negative 8x would give me negative 32x squared. Alright, so then negative 8 times 3 is negative 24x. And I want to have negative 4x, so I'm going to have to add 20x to that. 4 times 5 is 20, and then 5 times 3 is 15. And good, that worked out. So 15 is what I want. That's what I have in the box. So now I'm left with 4x squared minus 8x plus 5. And that's a quadratic that I can solve if I set it equal to 0. I'm actually going to use just the quadratic formula for this. So that's the opposite of b plus or minus the square root of b squared, so negative 8 squared, minus 4 times a times c, all over 2 times a. So in my first step of simplifying, I just simplified the stuff in the square root, and 64 minus 80 is 16, or negative 16. And it's crappy that it's a negative number, but at least it's a perfect square. So this would also be 8 plus or minus 4i, because it's imaginary, over 8. And I can simplify this a little bit more. Let's see, if I did 8 over 8, that would just be like 1, and 4 over 8 is like 1/2, so 1/2 I. And now at least it's written in standard form as well. So we found all of the zeros now because there's 2 of them. There's 2 imaginary zeros, and the last one was just x equals the one from the graph, which was negative 0.75, or negative 3/4. Let's just write it as a fraction. And there's our 3 solutions. Now we're going to look at a few more problems where we're going to build some functions looking at the given zeros. In the first problem, we have 3 as a zero, so that means x minus 3 would be a factor. And then we have plus or minus 2i. So they always come in conjugate pairs like that. So I'm going to have x plus 2i and x minus 2i as factors. I'm going to choose to multiply these 2 factors together first because they're conjugates, so it's going to give me a nice result. So x times x is x squared. I'm not even going to multiply these 2 boxes together because they're going to cancel out, and this would be negative 4i squared, which is really a positive 4. So that gave me x squared plus 4, and now I just have to multiply that by the remaining x minus 3 from the beginning. So this gives me x cubed, this would be 4x, negative 3x squared, and negative 12. So my final answer is just x cubed minus 3x squared plus 4x minus 12. The next problem looks very similar, but it's 3 plus or minus 2i. This is just 2 complex numbers. So my final answer is going to be a quadratic equation. So one factor would be x minus 3 plus 2i, and the other one would be x minus 3 minus 2i. So remember, with conjugates, the only thing that changes is the sign in the middle of that complex number. So now let's multiply these together. It's going to be 3 by 3, which seems complicated, but again, since they're conjugates, a lot of stuff should cancel out. Alright, so this gives me x squared, negative 3x, negative 2ix. Here this is negative 3x again, a 9, and then this would be positive 6i. Here we have 2ix, so that's going to cancel with the negative 2ix. Here we have negative 6i, those will cancel. And then 2i times negative 2i is negative 4i squared, which is just positive 4. So altogether, this gives me x squared minus 6x if I put these together. And then I had a 9 and a 4, which go together to make 13. And there's my quadratic equation that came from those 2 imaginary solutions. And the last problem has quite a few more solutions. We have 1, 2, and then here it just lists one imaginary solution, 3 plus I square roots of 2. So you have to be smart enough to realize that there's going to be a conjugate imaginary solution. It'd be 3 minus I square roots of 2, because again, they have to come in conjugate pairs, because imaginary numbers come from taking the square root of something, which means a plus or minus would have to be in front of it. So it actually has 1, 2, 3, 4 solutions, even though they only wrote out 3 of them to start out with. So the first factor would be x minus 2/3, which actually I'm going to fix that right away by multiplying a 3 in front of it. That would give me 3x minus 2. If I distribute that in, the 3's would cancel. So 3x minus 2. This solution, negative 1, would give me a factor x plus 1. And then these last imaginary solutions, it would be x minus 3 minus I square roots of 2. And the other one would be x minus, again, but then 3 plus I square roots of 2. Again, I'm going to choose to multiply the 2 complex conjugates together first, because I'll get a nice result. And I just did that really quick here, but just to double check that you have all the same things, these would cancel. The 3i squared of 2, negative 3i squared of 2 cancels. And then in the last box we had negative I times I, so that gave me negative I squared. And the square root of 2 times the square root of 2 just gave me 2. Remember, I squared is negative 1, so that last box is positive 2. So from those 2 factors, I have x squared minus 6x, and then I had a 9 and a 2, which would be plus 11. So now I have to take that trinomial, and I still have to multiply by both of these factors in front. I'm actually going to take those 2 and multiply them together here, and then I'll just have a quadratic times another quadratic. So again, I just did that real quick for you, and I got 3x squared plus x minus 2 if I combine those like terms. So now I have to take those quadratics and multiply them together. So here's the box with a trinomial times a trinomial, and I'll just do this real quick for you again. But try it on your own and then just double check your answers with mine, and now let's just combine like terms. So 3x to the fourth minus 15x to the third. I have 3 terms here that are all quadratic, so 33 minus 6 would be 27, minus 2 more would be 25, so plus 25x squared. Let's make this look a little bit more like a cubed. 11 plus 12 is 25x, and then minus 22 at the end, and that's your final answer. Finally, we're just asked to solve 2 quadratic equations using any method. You could either graph it if you want, but you don't always have access to a graphing calculator. So you could try factoring or quadratic formula or completing the square. Not many people like to do completing the square, but this one is set up for us perfectly to do that. So I'm just going to write x squared plus 4x, leave myself a space, equals negative 8, and then a space. So remember, we take x and then half of that b value, so plus 2, square it, but then 2 squared is 4. So then you have to add 4 over here as well. Negative 8 plus 4 is negative 4. So remember, x squared plus 4x plus 4, that could factor into x plus 2 squared. And then over here we have negative 4. So there we go. This is all a true statement there. So now I just have to solve this by taking the square root of both sides. So I get x plus 2 equals plus or minus 2i. And then just subtract 2 from both sides. So negative 2 plus or minus 2i are my 2 imaginary solutions to that quadratic. Alright, this one is not set up for completing the square, and it kind of sucks having a 5 in front, so I'm just going to use a quadratic formula. So opposite of b plus or minus the square root of b squared minus 4 times a times c, all of that over 2 times a. So I got 64 minus 220 inside the square root. And now if I simplify that, so 8 plus or minus, 64 minus 220 is negative 156, all of that over 10. And now I have to see if I can simplify the square root. So I'm looking for a perfect square that goes into 156. And 4 was the first one that I tried, so I figured out that I can get 8 plus or minus the square root of, I'm going to change this into negative 4 times 39. Again, all over 10. So this helps me because the square root of negative 4 is 2i. So I can write this as 8 plus or minus 2i, and then still the square root of 39, all of that over 10. And for the last step, there's one more simplifying step I can do. This is even, this is even, this is even. So I can pull a 2 out of everything on top. That would give me 4 plus or minus I square root of 39. And then on bottom, I could factor that 10 into like a 2 times 5. And again, since this is broken up by multiplication on top and bottom, it's okay to undo that multiplication by dividing. 2 over 2 cancels, and I'm left with this as my 2 solutions. But I'm going to write it out nicer. So I'm going to write 4 over 5 plus or minus the square root of 39 over 5, and then I next to it. And now it's in standard form. So this is a really long lesson, I apologize about that, but thanks for hanging in there. This is a really important lesson in all of algebra and calculus. We started with something called the fundamental theorem of algebra. So there was a lot of information in here. I know it was long, but if there's something that you're confused about, feel free to go back and watch it over again or ask me questions.